Today we're starting on chapter 7, deals with decimals. We've talked about fractions, we've talked about integers, we've talked about rational numbers, which are fractions. Now we're going to look at decimals. What are decimals? What does the word decimal mean? Wild guess. Do any of those letters look familiar? Deci. What's deci in Latin? Right. Tenth. Decimals refer to numbers that are smaller than 1. Let's look how numbers are structured. What is our base system for the numbers that we're using? What base? We talked about bases. What base system are we in? Which one? What base system is that then? Base 10. Very good. If you ever forget, count the number of fingers you have. Each group of numbers, the single digit numbers, go from 0 through 9. Those are 10 numbers. Then it goes from 10 to 19 before it switches to 20 to 29 to 30 to 39, 40, 49. So we're a base 10 system. The decimal point separates numbers that are larger than 1 from numbers that are less than 1. So, for example, and so on and so forth. What is 10 to the 0? What is anything to the 0? Basically, x to the 0 is the same thing as 5 to the 0. Anything to the 0, so that's the ones column. What is 10 to the first power? This is the tens column. 10 squared? Yeah. 10 times 10 is the hundreds. 10 to the third is the thousands. 10 to the fourth is the 10,000s. Easier way you can think about this is if you have a base 10 and you raise it to an exponent, the exponent tells you how many zeros are after the 1. 10 to the third, there are 3 zeros. 10 to the second is only 2 zeros. So if you have a base 10 raised to a power, then the exponent just tells you how many zeros are behind it. So what would that number be? Mm-hmm. It would be 1,025. You have 5 in the ones column. That's the first. You have 2 in the tens. You have nothing in the hundreds, and you have 1 in the thousands. So you have 1,025. Then you have your decimal. Now, how do we make things smaller? After the decimal, what we have here are negative exponents. What do negative exponents mean? What do they represent? We discussed exponential powers. If you have a negative exponent, you simply change the position of where it is on the dividing line. If it has the negative numbers on top of the dividing line, you put it to the bottom. If it's on the bottom already, then you bring it up on top and drop the negative. The negative exponent does not make the number negative, it just makes it a fraction. So 10 to the power negative 1 is the same thing as 1 over 10 to the first, 1/10. Next one is 1 over 100, 1 over 1,000, and 1 over 10,000. These are the numbers: 1/10, 1/100th, 1/1000th. So now our number looks like this. How would you read that? You read the left side, the normal 1,025, and 345 1,000ths. You always read it to the last decimal. So it's 345 1,000ths. If you only had 0.34, you would read it as 1,025 and 3/4, or 3/400ths, 3/400ths. But you always refer it to the last digit. These other ones don't have a name, because that tells you how large it is. I mean, that was. Here's a question. What what do kids see first in elementary school? What type of numbers? Mixed numbers or decimals? Mixed numbers. Way before decimals. And then they're introduced decimals really quick. without much thought about it. Because think about it. We have to think of a whole new way of presenting decimals. How would you represent this number using manipulatives? Or how would you represent this number? So look at this one. Because we can't do this until we learn how to divide. So that's what we're stuck with us now. How would you teach that to your students? What does it mean to them? Ah, stuck. We're dealing with 1/4. We're dealing with 1/4. So each of these have to have 4 pieces in there. This number tells us that we have 2 of the circles already filled. This one tells us we only have 1 of them filled. What's another way of reading this? We started off with 2 and 1/4. So we have 2 full ones, and one of them only has only one of them completed out of the 4 pieces. So we have 2 of them that have all 4. What the kids are going to do is, since each of these are divided into fourths, how many pieces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2 and 4 1/4 is the same thing as 9/4. This is also pretty much how you would introduce division to the kids. So, okay, let's look at this. 9 divided by 4. How many times does 4 go into 9? Well, yeah, so we do this. We make 4 boxes and start filling them in. It goes in there twice with 1 left over out of 4. Let's see. Oh, let's look at the manipulatives. How would you represent this using blocks? Let's try that. We do it the same way we just did with the circles. So how much would 1 block be worth? Yeah, this would equal 1/10. If we had 10 of those, 6, 7, 8, 9, 10. So if we had 10 blocks, what would that equal? Right, because we count all the top ones, we get 10 over 10, which is equal to 1. So 1 stack like this would equal a 1. So for our number, how many stacks do we need? Yeah, so we need 2 stacks. And how many single blocks? Just 1. Okay. How would you write this number? What would that represent? Ooh. Remember, we're dealing with how much you have to first figure out what the single block is. This is each 1/10. So these would be what? Ones. So these would be, if we had 10 of those, that would be a 10. So how many 10s do we have? So it's 20, 4, and 7/10. Yeah, because then we can convert those to decimals. Once we introduce them, that these are what each decimal represents another one of those. You're looking at it. Because you have to first define what these blocks are before you get going. Earlier, these used to be ones. Then it'll be 247. But now we're talking about decimals. We define these as 1/10. What if these, instead of 1/10, what if they were 1/5? What would be our number? Remember, there are 10 of them in here. Remember, each of these have 10 blocks in them. Each of these have 100 blocks in them. And if each one was 1/5, what would that number be? We're changing the number system here. Because once you reach 5 of them, then that becomes a 1. So we have 2/5 left over. Remember, these are 10s. So we actually have 1, 2, 3, 4, 5. 1, 2, 3, and then this one. So that one now becomes another stack of 5. Since they're 1/5, the ones are 5 units tall. Since these are 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So at every 5, we'd get a next digit. 1, 2, 3, 4, 5. One, two, three. 1, 2, 3, that's 4. That would be that number. But remember we talked about different bases earlier? We now are, since we're dealing with 1/5, we now are dealing with base 5 number system. So every time, once you reach the 5th one, it moves over to the next column over. And since we have these 4 and one more comes in, that's we get a 0, it moves it over. And you wouldn't read this as 1042 because 1042 is base 10. You would read this as 1042 base 5. But that would really confuse your kids. Don't do that. Well, do kind of this kind of thing. We did the base systems a month and a half, 2 months ago. How would you represent that using base 10 blocks? How many cubes would you need? Very good. Why is that?
Each decimal or each tenth would be a block.
Mm-hmm.
So then that means each corner will be 10.
So there'd be 5 of these with 10 of them in there. Each stack has 10. There's a decimal. And so those are the individual ones. We'd have 54 small blocks, right? Very good. Yeah. That's why theory of my part is that's why I think students get confused with decimals. Because we spend so much time making these ones and these tens and those hundreds that it's hard to get that out of your brain. So instead of this is 5.4, we're looking at 54, which is kind of what it is. 54 10, we have 54 1/10 pieces, which is equal to 5.4. But that's way above the head of the kids. Let's talk about converting numbers to other forms. So I'm going to give you a decimal here. For example, the one we're going to use is, well, use 5.4. How would you expand that? Using fractions. It's what we just did. The one we just did, this is how you do it. Because what does the 5 represent? It's just the whole number. And you add to it, what is this decimal 4 number? How would you represent that? Which that equals 5 4/10. Which is the common. representation. How about that one? How would you represent that one?
Well,
Well, yeah, start with the first number. This is that's why you always put a zero in front of the first decimal if there's nothing there. So it's 0 integers. And this first one is the tenths. We have no tenths. And the next one is 2 over hundredths. So that one equals 2 over 100. So the first one is 2. Then we have 0 over 10, 1 over 100, 0 over 1,000, 3 over 10,000. All we're doing is adding another 0 on the bottom as we go further out. So how would we write this as a single number? We have 2. Remember, we always use the biggest denominator. So the denominator is going to be over 10,000. And so what's over 10,000? 103. Does that look good? It does, but it looks weird. So how do we convert this to a improper fraction?
you got 20,000.
Yeah, because 2 times, so we have 2 times the bottom number plus the top number all over the bottom. So we have 2 times 1 is 2 with 4 zeros behind it plus 103 over 10,000. So how would the kids add these two numbers together? What do we always teach them to have to do? Right. Line them up. So we have that. So the ones, the tens, and then. So equals 3, 0, 1, 0, 2. How about a negative number? The negative doesn't matter. Just take the negative outside. So we have 3 plus 6 over 10. This equals the negatives out in front. I add those two. I got 3 6/10. Again, from mixed number to improper fractions, put the negative out in front. 3 times 10 plus 6 over 10. 30 plus 6. So the negative is just a number that's out there. So treat that number and then put a negative in front of it. Let's look at example 1. Remember, we've taught the students how to convert mixed numbers to improper fractions. Example 1. A, we have 25 over 10. B, we have 56 over 100. And 205 divided by 10,000. Convert to decimal. So how would you do the first one? Without dividing, just yet. Remember, we have to teach them what all these numbers mean. What is 25? We're teaching the opposite process we did. 25 is what? It's 20, which is 2 times 10. Or let's do it by pieces. 20 plus 5 over 10. 20 is 2 times 10 plus 5 over 10. We can split them up now. 20 times 10 over 10 plus 5 over 10. The 10s cancel. We will introduce also the rules about multiplying and dividing by tens. What are those rules, you think?
Whatever the number multiplied by 10, it's the same number, just added, yeah, add a zero to them.
So what are you doing? You're taking it, just add it. You're telling me what are we doing? We're dealing with decimals here. So what do we do with the decimal? When you divide by 10, move the decimal left. How many spaces? The number of zeros on the bottom. In other words, 5 divided by 10. There's only one zero. So we know the decimal is right there after the 5. Since it's dividing, we move it to the left. So this becomes 2 plus 0.5, which then makes it 2.5. So when you're dividing, you move the decimal left, the number of zeros you have on the bottom. Since you only have one zero, you move it one space to the left. So with that rule for dividing by tens, this is dividing by tens because it has a 1 and some zeros behind it. We could just use a shortcut. And where's the decimal right now in the number? After the 6. Yeah. If there's no decimal written in the number, it's always after the last digit. Because if it doesn't have anything behind it, you don't need the decimal anymore. So here, since we're dividing by 100, we move it to the left how many spaces? 1, 2. So on this one, we have the decimals after the 5. How many spaces do we move it to the left? Yeah, since there are 4 zeros, 1, 2, 3, 4. Since we moved it an extra space, we have to put a 0 there. But we had to use a simple example to get to the rule. Because you're dividing by 10, you move it to the left one. What do you do when you multiply by tens? Yeah. Of zeros. So if we had 35 times 10 or 100, we have to first ask, where is the decimal on this 35? After the 5. Since I'm multiplying by 2 zeros, I got to move it to the right, 2 spaces. So whatever is there, I put zeros. Because there's nothing there, I put zeros. Is that a true statement? There's nothing there. Because the number 35 actually looks like this. It has an infinite number of zeros behind it. It doesn't that just doesn't do anything for us. So when we multiply this number times 100, now we move the decimal 2 spaces. So now we have 3,500. And since there's no number after that decimal, I don't have to put those numbers there. Now you see why kids have a hard time with division. The rules not change, but they morph into other rules. The next example. Example 2. Express each as a decimal. Express as a decimal. Remember, we have to stick with the rules we've just been talking about. Since we're talking about decimals, what has to be the number on the bottom? Decimals are 1/10. So we have to make the bottom number some factor of 10. So what do we have to, what times 2 gives us 10? 5. Since we have 6 2's, then we have to multiply top and bottom since 2 and 2 to the 6, 5, since they both have the same exponents, I can combine them by the rules of exponents we talked about. Two times 5 is 10 to the 6. Five to the 6. Okay, this is a ridiculous number. So we'd have to, if we take a piece of paper, we can make the kids 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 750. And keep on going till we get that. What we would end up with is something like what's 15,625. That's 5 to the 6. Over 10 to the 6. So we'd multiply these two, we'd get 109,375. So we're dividing by tens. When we divide by tens, which direction do we move a decimal? To the left. How many spaces? The exponent tells us how many zeros we have. So we have 109,375. The decimal's over here. 1, 2, 3, 4, 5, 6. So our answer is 0.109375. So that's our goal. If possible, make the bottom some factor of 10. How about the next one? Do they have the same exponents? No. So we have 4 5s when we have 3 2s. How many more 2s do we need so they're equal? Nope, we have 3 already. We need to have 4, so how many are we missing? Just 1. So we have to multiply the top and bottom by 2. Now we have 4 2s and 4 5s on the bottom. So we have 2 over 10 to the 4th. We have to move it to the left 4 spaces. 1, 2, 3, 4. So we have to have 0, 0, 0. So any questions so far? How would you do the next one? Yeah, these first 2 were nice enough to be separated for us. So what do you think we have to do for the next 2? Yeah, we have to factor them out. So we have to take 125. Since it ends in a 5, we know it's divisible by 5. 5 goes into 12 how many times? Twice, with 2 left over. 5 goes into 25 5 times. And 25 is 5 times 5. So 125 is the same thing as 5 times 5 times 5. So what are we missing? What do we multiply to 5 to get 10? How many 2s do we need? 3. So we have to multiply top and bottom by 2 to the 3rd. What is 2 to the 3rd? 2 times 2 times 2 is 8. And now we have 5 times 2. They're both to the 3rd power. So we got to move it 3 spaces to the left. There's a 0. There's a 0. And there's our answer. Do the same thing with the last one. Since it ends in a zero, what do we know it divides by? 10. So 10 times what? 25. 10 is made up of 2 times 5. 25 is 5 times 5. So we have 7 over 2 times 5 to the third. What are we missing? Yeah, we only have 1 2 there. How many are we missing? We're missing 2 2s. Because we have to have 3 2s on the bottom. Oop. So we're missing 2 more 2s. So we have 3 2s and 3 5s. Two squared is 4. So we have 28 over 10 cubed. One, 2, 3. So the answer is 0.028. Pretty interesting. So if it's possible, make the bottom into some numbers that's factorable by 2 times 5. Which brings us to the next topic in this section. Defining terminating decimals. What does it mean by terminating decimals? The number of decimal spaces is finite. There's an end to it. For example, 1 over 4 is 0.25. It stops. 1 over 3 is 0.3333 forever, which we write as 3 bar, 0.3 bar. This bar says that number or that pattern repeats. If we had 0.25 bar, it would be 0.25, 25, 25, 25 forever. So instead of writing 0.25, 25, 25, 25, I just write it however large the repetition is. How do we know if a number is terminating decimal? The theorem, 7.1. A rational number, A over B, in simplest form can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 and 5. A fraction in its simplest form, meaning reduces as far as you can go, can be written as a terminating decimal if and only if the prime factorization of the denominator only contains the numbers 2 and 5. Does that make sense? Let's see. Example 3. Which of the following have terminating decimals? So what do you think? Is the first one a terminating decimal? By looking at it, you'd think what? Well, before you work these out, let's take a guess. Is the first one terminating? Yes or no? Without working it out, just by looking at these, without working anything out. What? Okay, because you worked this one already. I'm not gonna How about the next one? Okay, we're saying yes. How about the next one? Just by looking at it, it's zero thinking, just by looking at it. What do you think? Because I know you guys are trying to go through this and factor out the bottom.
Yes.
How about the next one? Let's see. The number 8 is made up of what? 4 is made up of. So, is the prime factorization denominator containing no primes other than 2 and 5? So is this one a terminating decimal? Yes, because all the bottom is made up of are 2's. only numbers you can have in the factored form are 2 and 5s. So yes, the first one is a terminating decimal. How about B? 250. Well, we just worked that one out. 25 times 10, 5 times 5, 5 times 2, only 2s and 5s. So yes, it's a terminating decimal. It's 2 times 5 to the third. $28 can be divided by 2. 14 is 2 times 7. Right. Hold it. Is this the simplest form? Because 21 is made up of 3 times 7. 28 is made up of 2 times 2 times 7. The 7s cancel. So yes, that one's because all we have left on the bottom are 2s. We have to simplify it first. Three, 8, 4. 1, 9, 2. 9, 6. 4, 8. 24. And 37 is a prime number, so this 3 doesn't cancel. So it's not a terminating decimal. How would you order terminating decimals? When ordering terminating decimals, you have to look at each position individually. So they both have a 2, 4, 5. They both have a 1 and the next number. The next one here is a 1. This one's a 2. So this number is bigger than this one. So that's all there is to terminating decimals. Well, no, we're not done yet. We have another section to do. We still have half an hour to go. Now we're going to look at